Hello, hello, howdy, howdy. Yes. Oh wait. Okay, I'm gonna catch up. I'm already about. Hello, Gabriel. Howdy, howdy, Kat. Hello, Rachel. Hi, Skyla. Hello, Michaela. Hi, Crystal. Hey, Kaveza. Hi, Kaliana. What? More people. Okay. What is that? Oh, hello, Veronica. Wait, why can't I do this? Wait a minute. Sorry. Ah, okay. Okay. Hello, hello, hello. Okay, okay. Hello, hello. Yes, hello, hello. Okay. Um, oh, hello. Yes, hello, Lola. Thank you. I appreciate it. Hello, hello. Okay, who else? Oh, sorry. Hey, Jesse. Sorry about that. Um, who else did? Yes, well, I think that's everybody. Yes, hello, hello. It is good to see you all. Um, I feel bad for you that you're inside right now because it's kind of nice out. Take your computers outside into the lovely green pastures of Queens or whatever, wherever you are. Oh, there you go. All right. So, okay, windows open. That's a start. Oh, wait, it just reminded me. Um, okay. Yeah, just everybody, let's just go outside. Let's put our masks on and take a big whiff of the fresh, clean air of our masks. That'll be good. Okay, so oh God, who's not getting sick of masks? Okay. Uh, okay, I think that's everybody. Hello, hello. Yes, hello, Soha. Thank you very much. Appreciate it. Hello. Okay, I think we're. Oh, and the light. Pardon me. Okay. All right. Let me first address the thing that might already be obvious because you didn't. Well, so you got some stuff back from me this week, and some of you, but what you didn't get back from me this week, and you might have noticed, and I'm saying this with a smile, but so you did not get your test back from me yet, and that is bad. I'm not happy about that. That is on me. I'm actually hoping, depending on what we're doing, I mean, depending on how today goes, we are going to do more individual work today, and I am sort of hoping maybe, but this never works, but I'm going to try to actually finish them while we're all working today. It's there now. It's now a little bit ridiculous that you don't have them back yet, and it's totally my fault and reflects nothing but my badness. And I do want you to have them soon so that we can like not have anxiety and stuff like that. I have no excuse or no good excuse. There's no such thing as a good excuse. Um, but I, but it, if we can, I'm going to try to finish these, as I just said, while we're teaching, and then get it back to you for today. But if I don't, I don't. If I will tell you right now too, because I know this semester is starting to move on here. There's 1,000 reasons I want you to have them, and 1,000 reasons that I feel ashamed that you don't. I'm not trying to over talk it or over dramatize, but for those of you who are worried about grades and stuff like that, I do. One of the reasons I want to get them back to you is just in case there is a problem in any of them, just in case just in case any of you didn't do well or didn't do as well as you'd like, or so, there still should and will be an opportunity for some kind of test corrections or something. Like, I don't want the clock to run out and you be standing there with no chance to rectify. Of course, we also have a final exam, but believe me, I'm committed to the idea that before you take your final exam, you should still know where you're standing in the class and how hard you have to kill yourself or not for the final exam. So that is all on my mind, and it is concerns that I take seriously. There's not much more I can say until I get them back to you. I'm sorry. I'll look in the chat in a second. Actually, I'm going to intentionally avoid the chat for a moment. I did have one thing I'm pleased about. I mean, we're still in COVID here. It still stinks. I still hate it. You hate it. But in the little cracks in the edifice that maybe are existing in COVID, or that we're all getting to invent because we're just like running out of steam and stuff, I will say that I'm delighted that finally, like the Walters, I have gotten, we were able to get together. We are starting to get together again in real life, which is long overdue. I mean, I love hanging out with them. I love hanging out with my son. So we had a big session last week where we played tons of video games and had lots of fun, but also talked a lot about your exams and where you are and stuff like that. So, you know, I don't know what that means, but we care about you deeply. We are going to get these exams back to you. It's on me to finish them. But so far, it seems like we think you're all doing well. And again, if anything has gone awry for any of you, there will be a chance to rectify. You won't find out after it's too late or something like that. There's just, I don't believe in too late. That's like my long, I mean, that doesn't help anybody right now, but that's just the truth. Let me just look in the chat. Okay. So first of all, good morning or good afternoon, Quasi. And okay, so I apparently totally did not get the reference. I'm almost afraid to ask. I totally missed. I don't get the reference, and I'm afraid that even when I still might not get the reference. I hate feeling old.
My background is from a very famous horror film.
Oh wait, don't tell me. Wait, I wasn't looking at your background. Is it The Shining? It is. Yeah. Oh, sweet. Okay, sorry. I did. Okay, now I feel a little bit vindicated. And the minute you said, okay, I wasn't even looking at your background and said, okay, I love The Shining. That's awesome. You know, one time, in fact, I had someone in the class someone attempted but then gave up. Was going to do a research project one year on the continuity errors in The Shining, or the what do you call it? There is this whole. Well, anyway, you probably know better than I do. But no, yeah, great. In fact, no, I will say this. Oh God, how many years ago was it this point? It was definitely before COVID. There was one year where I had the whole physics department program meet me in our lab late at night for something we all had to do. And it was Halloween, but I couldn't meet them until after I took my son trick-or-treating. So like they were waiting for me forever at John Jay in the lab, like it was completely inappropriate, outrageous on my part that I had them all waiting for me for so long, but they were all gathered. They were done with trick-or-treating or whatever they do. But it was Halloween. They were all waiting for me, and I showed up really late at night. And when I walked into the lab, what they had been doing to spend time until I got there was they all totally put The Shining up on the big screen in the lab. And it was really spooky to walk into that experience. But yeah, no, great movie. Yes, okay, that totally. Okay. Okay, fair enough. And he is a great writer. He is a great writer. I confess I've never read the original, but I believe it. I mean, there's two things that dude understands. God, you guys get me off the top. You know, this is going to happen. I'm going to be so guilty about not having your exams. I'm going to spend 2.5 hours talking about nothing, I'm sure. But no, that won't happen. But one thing about, God, now I'm forgetting his name, Stephen King. Like, yeah, he totally understands horror clearly and understands like the dark side of darkness. But there's one other thing that guy so understands. It's little children. I mean, there's some part of him that never forgot, in my opinion, like what it means to look at the world as a child. And I think that is both in the scary way and in the not scary way. And I think that is definitely one of the qualities. But anyway, whatever. Yes, great references. Okay. Okay. What we're going to do today. Well, I'm going to check in with you guys on one thing, make sure I'm not crazy about what's going on in the lab. But what we're going to do, we spent all this time last week sort of putting down the ingredients of the Doppler effect. And I believe, if I'm not mistaken, even your most recent motion or your most recent like lab simulation thing with Walters was a big probing of one of these ingredients. I will confirm that in a second. But if I'm not mistaken, we spent all this time laying down the ingredients, but then I left you last Monday saying, oh, finish this for homework. And, you know, I didn't put it in the portal, and who knows if you did or not, but where we left off last time, and I'll show you the notes in a second, like we're going to do, I gave you numbers. I gave you a numerical example of what we're going to call case 1 of the Doppler effect. I mentioned last time, and I will remind you that there, in the standard understanding of the Doppler effect, there's 4 different cases. What's going to happen today, unless I'm mistaken about what's been going on in lab, what's going to happen today is after I refresh you all, or after we refresh ourselves of exactly what the cases are and what the numbers are, I am going to turn you guys amongst yourselves, like in the breakout rooms or whatever, and I'm going to ask you to work through these to get answers to the 4 different cases. And then we are going to discuss them sort of board meeting style, or whatever you call it in lab these days. So there's going to be a lot more individual work, hopefully today than usual, partly because the Doppler effect is that kind of thing. And then also partly, hopefully I can make more tracks with your exam while that's happening. I won't go anywhere. I'll be right here to answer questions and all that. But let me confirm that I'm not crazy. Well, no, too late for that. Let me confirm that from what I think, in the very last motion you did in lab, it was not about electricity, right? The very last motion you did I don't even, in my opinion, was about Galileo's principle of relativity, but you might not have called it that. Was it the thing of like looking at the cube moving from 2 different perspectives? Is that right? Okay. And yes, okay, cool. Thank you. Okay, cool. Thank you. And well, I guess, all right. So let me put, good. That's what I was hoping. That's what I thought. That means that what I have in mind for today is correct. But maybe just to take a moment, like I think of that as Galileo's principle of relativity, but is that how, could you just briefly tell me like either what you called it or what the conclusion was, or anybody give me like that was part of it. Oh, okay. That was part of it. Yeah. Does anybody want to just briefly summarize briefly summarize what they got out of it, or what they think they were supposed to get out of it, or what the last thing you established from it was? Okay. So, yeah. Okay. It's all relative. Yes. Okay. Okay. Oh, very well said. Both of you. Thank you, Kat and Veronica. That totally, yes. And there's still more people coming. Sorry. Okay. Yes. And good. Okay. I want to hear about that in a minute. And actually that's good to know. So first, on the first part of the lab, yes, I mean, we are then on the same page. I mean, you people and I, like what I will continue to call Galileo's principle of relativity, and which I'll write out more formally if I haven't yet, is the principle that it's all relative, meaning that all velocities are relative. I'll expand on that or not as is necessary today. And yes, a good way of saying that in English, I mean, if I had to pick one phrase to show that you guys get it in English, in your way, like I absolutely would say that whoa. Oh, wait. Oh, wow. There's a lot in the chat. Okay. I'm going to totally check this. Great. I'm going to check this in a second. But yes, if there's one big way of understanding Galileo's principle of relativity, it is that, yes, all velocities are relative, or put another way, that any conclusion we ever come to about velocity, any measurement we ever make about the velocity of an object, totally 100% depends on perspective. Absolutely. I mean, good word for it. Perspective. Yes. Another technical word for that in physics is reference frame, or frame of reference, or even coordinate system. But absolutely, yes, if you got anything out of that part of the lab, that would be the thing to get out of it. That, in other words, and maybe I should write this down in a second, maybe I will, like one way of putting this is velocity is necessarily a relation between 2 objects. Velocity is never a property of one object. Velocity is not something that anything has. It is something that things have in comparison to other things, like literally and always and definitely. So literally, it is meaningless to say how fast is that thing going. You can only ask how fast is it going compared to some other thing. And if you, and like you're saying about perspective, if you switch what it is you're comparing it to, then you're going to switch your answer. And both answers are equally correct. I mean, that is the big takeaway, yes, of at least. And again, I might write that more formally in the way that we're doing things, but that is definitely the point, that velocity is relative, meaning it's a relation. It is not a property. Good. That's good. Now that's the first part of that. But then, oh wait, let me catch up in the chat. Sorry, hold on. Yeah, okay, it's all relative. Oh, and there's more people coming. Okay, there's another part of the lab, holding a wave, stuff like, oh. Lars stayed stagnant. Well, Lars, you know, he's kind of a no. Okay, yes, cool. It's all perspective. Okay. Yeah. Okay. The more you focus on it. Okay. Cool. 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 Yes, I agree with all that. That's good. I'm not even going to ask exactly what Lars did or did not do, but yes. Now, but what was the other part of the lab then? Or was it about waves? Is that, well, you tell me. Oh, yes, please do. Yes. Thank you for asking. Yes. Oh, okay. Oh, good. Oh, right. Yes, of course. Okay. Okay. But yes, do share the screen. But yes, good. Thank you, Veronica. And thank you, Kat. This is helpful. Totally. Oh, do I have to turn off? I guess I have to turn off my, sorry, hold on. Yes. Oh, this is, nobody needs, oh, okay. Now there's like two of me. That's the last thing anybody needs. Ah, oh, okay, cool. Thank you. Oh, awesome. God, it's almost like this guy Walters, I should really teach with him someday. It would be so awesome. It's perfect. It's like exactly what this class is. All right, right. Okay, so that, right. Yeah, you can keep scrolling. I appreciate it. Oh, oh, cool. He's so smart. Look at this. I mean, I don't know if this thrills you guys as much as me, but I'll tell you one thing about this class. You can't say that the lab and lecture are not connected, man. I mean, it's obviously not a coincidence, but okay, cool, cool, cool. Oh, good. Oh. Okay. And that's it. Oh, no, there's more. Okay, keep going. Sorry. Thank you. Wow. Okay. Thank you for sharing that screen. That is very helpful. And I have to say, yes, okay, that is exactly, I mean, if I had to dream up exactly what you would have talked about, that would be my dream. And I shouldn't be so excited because obviously that's the way life should be, but it generally isn't. So, okay, you are, and by the way, when I look at that and I get all excited, I'm not assuming that just because it's on the sheet, that means that every single one of you like perfectly, exactly understands everything. So I'm not, I get that that's not necessarily the case, but what you were exposed to, or at least what you were thinking about with him on Wednesday, is exactly good. It's exactly what I would have wanted you to be thinking about before we enter into today. So let me bring my screen back. And again, that does not mean that today will be a snap, but it means that at least it shouldn't strike you as a wild non sequitur or something. So, oh, one thing, this is very sloppy, but let me remind you this. So this is notes from last time. I mean, this page, you have this in your notes already, but I do want to remind you, maybe make it a little bit neater. Like everything that you were talking about with Walters or testing out with the cube thing, and then even with most of those questions that Kat just screen shared, like well, actually with all of those questions, this whole business of how fast is something going compared to something else, and what is the speed relative, all of that, again, I summarize as Galileo's principle of relativity, and where this principle first comes into existence, like, oh yeah. This comes from two books that Galileo wrote, one in 1626 and one in 1632. Galileo was born in 1650. Oh, I forget what. Sorry, in 1586 and died in 1642. And just for the record, he died in 1642. And then Christmas of 1642, Isaac Newton was born. So some say various mystical things about that. But this principle of relativity, that velocity is a relation, velocity is a relation between two objects, not a property of one. Like, what gives rise to the whole idea, why anybody would even say that or care about it or need to say it, it's all about justifying the belief that the Earth moves. Like, the summary of this whole principle in the end is the Earth moves, yet we don't feel it. ever, or experience it ever, or have any direct sensory like reason to believe it ever. And when I say ever, and when I say the earth moves, again, you may have thought of this 1,000 times in your life. And if I'm not careful, I could go on about this for 1,000 years. And I have in various books, but like, just note for the record that, you know, the floor underneath your feet is as stable as things get. Like your definition, our sense of stability is the ground, right? Nothing is more stable in our lives than the ground. And we walk around the ground and treat it as though it is still. Yet, for some reason, we were taught in third grade, and we've all accepted in some part of our brain ever since third grade or fourth grade or whatever, ever since the first time you ever were told to make a solar system model out of freaking fruits or tennis balls and basketballs or something, the first time you ever like put a big like watermelon here and called it the sun, and then put like a grapefruit over here and called it the earth, and like and tied them with a string or whatever, and had the earth like go around the sun. Like since that time, we've all been sort of in part of our brain accepting this apparent scientific truth that the earth moves, right? And you might have, depending on what legend you learned in school or what lesson you learned, you might have even heard something like that all of the dumb scientists before Galileo, or all the big dogmatic authoritarian like jerk face, and I'm paraphrasing, this is not actually the case, but you might have learned some story about how the big bad church like was so sure that the earth just sat still. But luckily the very smart and courageous Galileo like was, and again, I'm not saying this is the case, but I'm saying this is kind of the story that I was told, that Galileo like trusted the evidence of his own senses and the faculty of his own analytical reasoning and the brilliance of his own like freshly designed experimental scientific method. And that Galileo courageously like battled against the dogma of the blind dogma of the authoritarian church. And that Galileo was the one that courageously came in and said, no, despite your blind dogma, I say that the earth is moving and is going around the sun, not the other way around. And ever since then, thank goodness, we've all understood the true scientific truth that we got from the courageous Galileo. And we now thankfully like don't just blindly accept the dogma of authority anymore. Like I was taught a story like that, and I was taught that Galileo was a hero for rejecting ignorant authority and for brilliantly coming to his own scientific conclusion that the earth actually moves. But what I want to say about that, and I don't know if you learned that or not, but I learned something like that, or I feel like I learned something like that. But like, just for the record, okay, this very story, or this very like understanding of the earth moving and of science, is of course half the reason that half of people at an early age get completely turned off to science, or start like treating it in a very weird way, because the thing is, like, first of all, it's not idiotic at all to think that the earth doesn't move. It's not idiotic. It's completely reasonable to think that the earth doesn't move, because in every sense that ever, in every respect that ever meets your senses, the earth does not move. Furthermore, let me just go on to say, if I'm going to go on a rant about this, furthermore, it's not just like dumb people who are sitting around and like not thinking scientifically think that the earth is sitting still. Let me also point out that every bit of astronomy that was observed, measured, cataloged, analyzed, and predicted, like everything in astronomy, from the phases of the moon to eclipses of the moon and the sun, to the very complicated pattern of planets going past us, to the constellations, every bit of astronomy that was developed for thousands and thousands of years by every culture on the planet up until Galileo was accurate and right, and we still use today. Like whatever we know about the phases of the moon came from way before Galileo, and whatever we know about constellations and what they do came way before Galileo. And all the predictions that people made about like when Jupiter would be eclipsed by Saturn or this or that was all accurate and right, and still works today, and yet was all an astronomy that was based on an assumption that the sky was moving past us, not the other way around. Like nothing fell apart in those models or those theories until very, very detailed levels of things that we can or cannot talk about later. But my point is it's not just reasonable to think that the Earth isn't moving, but in fact, it totally works to think that the Earth is not moving. You can totally do astronomy that way and do it accurately and powerfully. But if you then say that the Earth is moving, I know I'm going on a rant right here, but just for the record, if you go and say, if you believe that the Earth is moving, you have to accept the whole picture. And the picture, the modern picture that says that the Earth is moving past the sun, like rather than the other way around, in the modern picture that says the Earth is moving past the sun, if you stop and ask yourself, well, then how come I don't feel it? Don't for a minute say to yourself what most people do, which is, well, I guess it's so slow that I can't feel it or something like that. Or I guess because of gravity, I don't feel it or something. No, 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 no. If the Earth is moving past the sun, you can Google this right now. If the Earth is moving past the sun, as we all do say in modern times, it's moving past the sun at speeds that average at 65,000 miles an hour all the time. Like the Earth is spinning on its axis at roughly 1,000 miles an hour all the time. And the whole freaking thing is zooming past the sun at 65,000 miles an hour all the time. That is faster than any airplane any of us has ever been in. That is faster than any rocket needs to go, even to go to the moon. Like typical rockets, escape velocity is like 45,000 miles an hour. If you believe that the Earth is moving, you're believing that it's moving through space past the sun all the time at like 65,000 miles an hour, and that sun that we're apparently hurtling past at 65,000 miles an hour all the time, that sun itself is not sitting still. It's not like we used to think the sun goes past the Earth, but then we intelligently, thank God, figured out that we were dumb before and realized, oh no, actually the Earth is going past the sun, and that's the end of the story. No. The Earth, you can say, is going past the sun, but the sun is going past the galactic center, the center of the Milky Way galaxy, at speeds approximating 650,000 miles an hour. 650,000 miles an hour. That's the sun going past the galactic center. And then we're going past that at 65,000 miles an hour. Like that's a lot of high speed continuous motion that apparently we're all just like calmly believing because we made a solar system model in third grade out of fruit. Like, and I'm not exaggerating now. I'm saying like, let's just get it straight. Even if Galileo was supposed to be a hero because he rejected just blind dogma and actually trusted the faculties of his own senses and his own reasoning. Well, when we accept the idea that the Earth is moving, all we're doing is accepting the blind authority of our third grade teacher. Like, I don't know about you, but my third grade teacher never gave me a freaking reason to believe that the Earth was moving. And because she couldn't and he couldn't, because there is no reason that is evident to my senses or to my daily life or to my daily thinking that would possibly lead me to the conclusion that the Earth is moving. If I accepted that the Earth is moving, I'm accepting it as moving at 65,000 miles an hour. And I'm only accepting it because my science teacher told me that in third grade. And of course, that is not what science is supposed to be about. Like at all. And it's actually why a lot of people get turned off because or why a lot of people end up just doing science and doing it well because they just think it's going to be one magic formula after another that we just accept on faith. That defeats the whole purpose of viewing Galileo as a hero. I actually do view him as a hero. He is one of my heroes, but that's why I spent a long time of my life trying to figure out why the heck he ever came to this conclusion in the first place. And the ultimate reason is just to like, and I'll look in the chat in a second. I know I'm just going crazy here, but this, if you like the other book, I've got whole books on this. The reason I'm going crazy on this is the basic, if you're going to say that the Earth moves at 65,000 miles an hour all the time past the sun, and yet all the time we sit around on Earth acting like terra firma is firm, then the reason has to be that the very act of motion itself, or the very idea of velocity itself, is deeper and weirder than we might have thought. The reason we can say that the Earth is moving at 65,000 miles an hour past the sun, while we can also say that it is moving at zero relative to itself, is because velocity is only and always a comparison. That what the Earth is doing compared to the sun is one thing, and what it's doing compared to itself is another. Or put another way, what I'm doing compared to the Earth is one thing, and what I'm doing compared to the sun is another, and they're both equally independently correct. Velocity is a relation, not a property. This boils down to saying the Earth moves and yet I don't feel it. or I could be in a high-speed elevator or a high-speed train or an airplane and not feel it. Like that's the nature of velocity. And okay, I'm babbling. Forgive me, I will pause for a second and I will look in the chat, but just to now bring this back mathematically, like so Galileo's principle of relativity is the thing that you were probing last week with Joe, and it does apply. It's like the character of velocity. It's not about the velocity of certain objects, and it's not about like what gimmickry we can pull off if we attach certain objects to other objects. It's just about the way motion works. And people did not unpack this until Galileo. Whoops, sorry. Oh yeah, hold on. Sorry. I guess that's a hint that I really should look at the chat in a second before I go crazy or drive myself crazy. But once Galileo established this in two really important books, one called Sidereus Nuncius and the other one called Starry Messenger, and the other one called Dialogue on the Two Chief Systems of the World. When he established this principle of relativity, we can say it a whole bunch of different ways. I mean, and we spend a lot of time in Physics 203 talking about all these different ways, but the first way is the laws of physics are the same at all velocities. The fourth way is this mathematical way. This is what I just want to remind you of or draw your attention to. Like, hopefully it seems consistent with what you did with Joe, and this is what we're going to use today to solve these Doppler effect problems. But just to remind you, like the thing that's on the screen right now, the thing that is on the screen right now is like the three case, and I guess I did tell you this last week, but sorry, just to remind you again or to reinforce, it's saying velocity is always a relation, not a property. Therefore, from here on in this class, or like in any physics class, anytime we talk about velocity, we're always going to put two subscripts after the velocity, because from now on, velocity is only meaningful if like you're comparing two objects. So if we let A, B, and C, let lowercase a, lowercase b, and lowercase c stand for three distinct objects moving at three distinct velocities, i.e. three distinct speeds, or at least three arbitrary speeds and three arbitrary directions, then what we're saying from now on, and again, I will take a breath in a minute, but we can view velocity in sort of three basic ways. One, like Roman numeral little one, is if you only have one object. Just look at object A. What's the velocity of object A relative to itself? We're saying it's always zero. Like an object by itself is always going at no speed compared to itself, right? Like that's the whole video game perspective thing. Put another way, if you want any object to have any velocity at all, you better introduce a second object to compare them. So now if we have a second object B, so it's like me and a subway train, or me and an airplane, or me and planet Earth, or planet Earth and the sun. If we've got two objects, A and B, whatever the velocity of one is doing relative to the other is necessarily, by definition, no matter what, just the opposite of what the other is doing to the one. If I'm going at 65,000 miles an hour to the east past the sun, then the sun is going at 65,000 miles an hour to the west past me. That's what Roman numeral 2 is saying. So that's like the two object case. Once you have two objects, then you can talk about velocity, but then your velocity is going to be a symmetric relation between the two. That's what the case number 2 says. Then finally, case number 3, the thing that we really, really need for the Doppler effect. So again, this is up the part like to reinforce, and the part where I'll pause. Part number 3, and I know I said this last time, but part number 3 says that if you have three objects, like me, a subway train, and New York City streets, or something like, or me, an airplane, and the ground, then the velocity of me relative to the ground is equal to the velocity of me relative to the airplane plus the velocity of the airplane relative to the ground. And of course that sounds obvious. And I remember you guys were saying very cool things about this last time, like about transitivity and stuff. It sounds obvious when I say it that way, and it is obvious in the obvious cases. It's obvious in the simple cases, especially when one of the velocities happens to be 0 or something like that. But the important thing here that we're then going to cross apply to the Doppler effect is that there are arrows written over these V's on purpose all over this page. Every time I put an arrow over the V, I'm trying to emphasize that we're not just talking about speed here. We're talking about the vector quantity known as velocity. Like we're not just talking about numbers, we're incorporating direction, i.e. negative signs and the possibility of more than one dimension. We're saying that each one of these statements is true independently along each axis independently. So even if we have a whole two-dimensional situation or a three-dimensional situation, everything along the x-axis will be true, while independently yet simultaneously everything along the y-axis, all the velocities will add appropriately along the y-axis independently yet simultaneously. But that very, very, very much includes negative signs, right? So if I walk south along an airplane that's flying to the north, you know, in effect, you would subtract my velocity from the airplane's velocity in order to get my velocity relative to the ground. That last one is what we totally have to use today in the Doppler effect. That's why it was circled before. Sorry. All of this together, so this equation, generally speaking, in this class, this is the thing that basically, you know, you were trying to drum into your own heads with Walters on Wednesday. And there's different ways to put it, but I refer to this last equation as a piece of GPR form number 4, like just so you know. And we put that together with the V equals lambda F equation in order to analyze all the Doppler effect problems. This thing is always true about velocity, always, always, always. And V equals lambda F is always true as long as you're talking about the velocity of a wave. So there we are. So we're going to put it together and do our thing today. I'm going to pause and look in the chat. Okay, hold on. Okay. Right, I can share screen. Yes, right. Cool. All right, and so I'm still looking at the chat, but yeah. So I'm just right now. What I just did was sort of back up to remind you of what. Right. No, let me say this again. The reason your lab with Walters had 2 parts is totally appropriate. It's one of the reasons I'm excited. Like the first part is to drill into us the character of velocity and how it is relative this way. And, you know, in theory, that's like just old physics. Like that's like the birth of physics, but we really need it here. But then the second part of what you're doing with Walters was now applying the concept of velocity to a wave. And yeah, one of your big takeaways I can see, I mean, from your sheet and from what you're telling me, the thing that sort of Walters is trying to remind you, or you're trying to remind yourself, is that once you have a wave, relativity still applies. Like every velocity we talk about has to be in relation to something. But with a wave automatically comes along, like a wave that I could throw a baseball from me to you, or I could throw a wave from me to you. Both things would have to follow the laws of physics. Like either whether it's a thingy thing or an unthingy thing, motions follow the law of motion. But the difference between me throwing a baseball at you versus me throwing a sound wave at you is that you can't have a wave without a medium. And what we're saying about waves is, so if I throw a baseball at you, you could talk about the baseball's velocity relative to me, or you could talk about the baseball velocity relative to you, or you could talk about my velocity relative to you. There's all these combinations. Same thing with a wave. If I throw a sound wave at you, you could talk about the speed of the sound relative to me, or you could talk about the speed of the sound relative to you, or you could talk about the speed of me relative to you, but there's also the medium that must be there if the sound wave is there. And the one thing we know about any kind of wave is it will have a velocity that is fixed relative to its medium. So it's like there's an extra frame of reference built into our analysis here that's automatically there and automatically fixes the velocity of the wave. That's, you know, what you were trying to drum in the second part of your lab last time. And let me be very careful to say that, so I'm saying, as you were saying to yourselves, once I throw sound from me to you, what we know in advance necessarily is that the speed of the sound must be a certain fixed constant number relative to the medium for that sound, say air. So yes, what we can rely on as a given is that sound necessarily travels at 340 meters per second relative to the air. We cannot make any claim like that about a baseball. There's just no equivalent claim. First of all, you don't even need to have air to throw a baseball. Second, if you do happen to have air, if it does anything, it's just going to get in the way of the baseball a little bit. But third of all, you certainly cannot say, oh, well, if I throw a baseball in air, necessarily, automatically, the baseball has to go this fast compared to the air. No, we don't say that about baseballs. But with a wave, we do. And just remember, though, but speeds are still relative. Velocities are still relative. So a sound wave necessarily has to go 340 meters per second relative to the air through which it travels. What it does relative to the source or what it does relative to the receiver then becomes the whole question and the whole set of options unto itself that we solve in the Doppler effect problem. There's no rule about that. No one's ever saying that sound has to travel at 340 meters per second relative to a speaker, nor does sound have to travel at 340 meters per second relative to a receiver. We just know that it has to travel at 340 meters per second relative to the air. And that's where the whole Doppler effect is going to open up. But okay, I'm still looking in the chat. Does that sound right? So that's why you did what you did. Okay, I think car beep. Right. So it's all about car beeps now that we're going to analyze again. What about teachers? Oh, okay. Well, I don't mean to make fun of your teachers, but I totally do. Well, anyway. Oh yeah, and by the way, and I do the whole big like story I just spun about Galileo. It's like a thing that's always, in my mind and and I've written papers about. But I am just making fun of generic teachers. Like I certainly don't mean to make fun of anybody's particular teacher, but nor do I mean to make fun of the church. I'm definitely not. I mean, really, I am trying to make fun. I do feel like the way it was presented to me was like science against church or science against religion or Galileo against the church. And no, but that is not an accurate or constructive way to view the history of it at all. No, and so first of all, the thing I'm making fun of it because I don't even think it's right. But also, right, you might have heard different versions. Maybe you did hear a version where the church didn't even care about what he said. I think that would be an exaggeration in another direction. Like, I don't think you're exaggerating if you say that, but like the church did care. I mean, the church was funding his work. I mean, to put it mildly, like he was very, very, very involved. Like, and he was a devout human being. I mean, I don't want to get into the whole thing right now, but it's certainly there was a relationship between him and the church. But I guess the one thing I'm very defensive about, I guess I just want to make clear right now, and of course, people's interpretations can differ, and nobody, like we weren't there, none of us was there, so it's all about piecing history together. But I guess to get personal for a second, like I have very, very strong feelings about the physics of this, as you can tell, and it sort of is my area of physics. That doesn't mean I'm right, but yes, I have very strong feelings about what Galileo was or was not saying, or what we're supposed to get out of his work. But also, just for the record, lest I accidentally offend anybody or something, I also have very strong feeling. Like I was brought up religiously, and I still care very deeply about religion. And just for the record or whatever, what I object to, one of the reasons I get so hot-headed about this is, even if Galileo did get into a tussle with the church, and he did, I mean, he did get in trouble with the church, and he did, I mean, there's no question about this. He ultimately, we did come before the Grand Inquisitor, and he definitely did have to sign a big confession statement that by signing it, he saved himself from execution and instead was put under house arrest for the rest of his life. I mean, he did live the latter part of his life literally under house arrest, like Martha Stewart. It's the only other person in history I've ever heard of who had this situation, but he wasn't allowed to go out of his house except for like very specific things. And more to the point, and this is definitely documented, and it's definitely as true as anything in history, it's definitely true that he was banned. Part of his agreement with the church is he had to stop doing astronomical research, and he had to restrict himself only to research on like inclined planes and with pendulums and springs, like in his little lab in his house. He wasn't allowed to do the stargazing thing anymore because, yes, he did get into trouble with the church. Like there's just no two ways about that. But that in no way means that you can't live in a world that with religion and science simultaneously. And it in no way means that if you want to believe in science, you can't be religious, or the reverse. And it in no way means that, I mean, I'm willing to offend people on this. Anybody who thinks that necessarily they have to make a choice between physics, like believing in electrons and believing in God, or, and again, I don't want to get too, but, or anything like that, that I'll say, I'm sorry, they're wrong. Like there's no, like, yes, there's certain, you know, you can take anything you want to an extreme, or you can have whatever opinions you want, but there's nothing in and of itself about physics beliefs, or in and of itself about religious beliefs or spiritual beliefs that have to be in conflict. If people want them to be in conflict, that's their business and they're making them in conflict, but that is their choice, just as much as a person like me can choose absolutely to hold both types of view in their brain and happily and get a lot out of both. And there's no my brain does not melt down and or explode just because I try to hold the two sets of belief are not necessarily in contradiction. They might incidentally be in some people's minds, but they don't have to be. And that is my opinion, but I do strongly believe that. Like, don't think that you have to cut out certain beliefs just because you let certain other beliefs in. But anyway, so wait. So okay, sorry. How do we feel it? Yeah, we don't feel it really. We don't. That's the thing. We don't really feel the Earth's motion. Certainly, we don't feel it past the sun. We observe the sun rise and the sun set every day. Like we observe things moving in the sky past us. So we know that there is motion between us. We know that we're not moving at the same speed as the sun. But it's kind of like when you're in an airplane, you can look out the window, like you can be in an airplane and it can feel all smooth and everything, right? Like once you take off. And the captain can say, okay, or I mean, like the flight attendant can get on the airplane thing and say, okay, like we've achieved cruising speed, and the captain has said that it has extinguished the fasten your seatbelt sign, and it is now safe for you to freely move about the captain. It is safe for you to now freely move about the cabin, and we'll be commencing beverage service in 10 minutes, and like you could start watching your movies now and everything. Well, like, yeah, that's already like a deep, weird thing, right? You're in this airplane. There's a point at which, even though the airplane is like 5,000 feet above the surface of the earth, and even though the airplane is moving at 500 miles an hour past the surface of the earth, for some reason, you can just like get up, like walk to the bathroom all casually. Like someone could say, hey, could you pass me the pretzels? And you just like pass them. You don't go like, all right, here we go, here come the pretzels, right? Like you don't do that. And if you're walking to the bathroom, if you jump up, you're not afraid that the back of the plane is going to slam you in the ass, right? Like you just walk around like it's normal. And in fact, then you put on a freaking movie or some whatever, like, or TV show now, like, in the back of the seat, you start watching a movie and you can literally like, and you're drinking your beverage and everything, and you could start complaining about how it's like a lame movie or you've seen it before or whatever, and literally dupe yourself into some sense of luxury as though you were in your own hotel room down on the ground, and like just act like everything is like la-di-da-di-da, even though you're hurtling through space at 500 miles an hour, right? Like that's crazy in and of itself. That's already a sign that something is very funny about motion. But you could look out the window and to be like, wait, or you could like fall asleep and then wake up and be like, wait, are we moving? Like, did we take off? Like, are we there yet? What's going on? And you could look out the window for evidence, and maybe you even see clouds moving past the window. But if you see clouds moving past the window, I don't know if you've ever thought about this before, but like you could see clouds moving past the window, but that doesn't answer any kind of question at all. You don't know if you're moving past the clouds or if the clouds are moving past you, right? I mean, something is happening, but you don't actually know whether you're actually moving or past the clouds, or the clouds are actually moving past you and you're actually at rest. And the ultimate thing is that the reason you don't know is because it's impossible to know, because it's a meaningless distinction. All that we can say about velocity is that there is velocity between you and the clouds. That's it. There's no meaning to saying you're actually sitting still or you're actually moving. Velocity is not a property that the airplane has. It's a relation that the airplane bears to things around it. Put another way, I mean, this is part of the whole Galileo thing. You could, in fact, try to be really scientific. You could say to yourself, okay, I'm not sure if we're moving or not. Like I'm kind of spaced out here, and actually I've had like way too many margaritas on this flight or something. So I'm not even like sure whether it's us that's moving past stuff or stuff is moving past us. So you might decide to be scientific and say, all right, cut the nonsense. I'm going to do an experiment. I'm going to do an experiment. Like, I've done my homework. Like, I don't believe in like just crazy made up philosophy. I believe in experiments. So what you do is you say, okay, for example, what you could do is say, all right, I don't know everything about gravity, but I know something about gravity. I know it tends to pull things down. And I know, like, if I'm just standing around in a hotel room or in a parking lot, if I'm just standing around, I know what happens when I drop objects. If I drop something, it'll land directly below my hand, like at my feet. It'll fall in a straight line, in other words, and land at my feet. That's what happens when I'm standing around. So you could say to yourself, oh, I'll do the following experiment. I'll drop something, and if it lands directly below my hand at my feet, I guess that means I'm just standing around, because that's what happens when I'm just standing around. But the problem with, like, you might think to do that, but the problem with that you might already be anticipating, and for all I know, you might be putting in the chat, but I'm just like ranting and raving here, so I'm not even looking. The problem with that is that the laws of physics are the same at all velocities. Like, this is Galileo's principle of relativity in its original form, is the laws of physics are the same at all constant velocities, which almost sounds obvious when you put it that way. Like, of course, that's why they're laws. Like they don't, like, laws govern how speeds work. They don't change at different speeds. The laws are the laws. So the laws are the same at all different velocities. Therefore, whatever experiment you ever do at one velocity is going to work out to the same result as at any other velocity. In other words, whatever would happen in a parking lot, if you were just standing around, you would drop something, it would fall to your feet. Well, even if you're standing, as you know from life experience, even if you are standing in an airplane that actually is going 500 miles an hour past the earth, if you hold something in your hand and drop it, it's still just going to land at your feet. And if you jump up, you're just going to hit the ceiling and come back down. The back of the plane is not going to slam you in the butt. The laws of physics are the same at all velocities, which means whatever velocities you're at, whatever experiment you do, it's going to work out the same no matter what. Which is why, in fact, form number 2 of Galileo's principle is, and this Galileo said this, that no experiment can be performed or even designed to measure the absolute velocity of a single object. Like, it's not a matter of technology or anything like that. You cannot even conceive, with all the technology in the world from the 1600s or the 21st century, no matter how much technology you have, you cannot design an experiment that would tell you whether the airplane's actually moving or not. You can't, because whatever experiment you design is going to work out the same way, whether you're moving or not, because the laws are the same at all velocities. So you literally cannot, so you drop something, and that's why you can be comfortable in an airplane and act like it's a hotel room, because all experiments, mundane or precise, work out the same as long as you're cruising. So there's no experiment you can do at all to figure out whether you're actually moving or not. And therefore, since physics is an experimental science and physics only believes what the data says, Galileo then concludes in his third form, says, oh, then I guess the idea of an absolute velocity of a single object is meaningless. Like, maybe it's philosophically interesting, maybe it's like psychologically interesting, but it's not physically, scientifically, measurably meaningful. There's just no such thing as the velocity of a thing. There is only the velocity of a thing relative to another thing. So I'm saying a lot, but back to the chat then, where I think Vadiata's question is great, but actually what I'm saying is we don't feel it. We don't feel the Earth's motion. All we know is that there is motion between the Earth and the sun. And Galileo, and in fact, this whole story that we used to think that the Earth was sitting still and that the sun's going past us, but then thanks to Galileo, we found out the actual truth is that the sun is sitting still and the Earth is going past it. No, that's not what Galileo concluded. That's not what we learned from Galileo. What we learned is that there isn't an absolute truth about that. This is the it's all relative baby thing from Walters. It's not. Yes, people used to think that the Earth was sitting actually and absolutely still and the sun was going past it, because that's a reasonable thing to think. What Galileo found out was not that the opposite of that is true. He didn't find out, oh no, actually the sun is sitting still and we are actually going past it. He found out that you could say it either way and it comes to the same thing. That's why astronomy still works either way. what he found out is it's all relative, baby. That we don't feel it, we can't feel it. Put another, I guess the last, I mean, I love Boniata's question, but what I'm trying to say is not only do we not feel the Earth's motion, but the real point of this whole principle is we can't, we never feel velocity. Velocity is not something that you ever feel. There's nothing to feel. What we feel is acceleration. We feel acceleration because F net equals ma. I mean, this is really how Galileo like leads into Newton. We feel acceleration. We feel changes in velocity. Like that's why you have to keep your seatbelt fastened when the airplane is taking off, when it is speeding up or landing, slowing down, or hitting turbulence and turning. Whenever velocities are changing, when there's acceleration, that can only happen due to net forces. Forces are interactions between objects. So put in super concrete or simple terms, when you're sitting in the airplane as it's taking off, oh, you feel that. First of all, you feel it in your stomach. And part of why you feel it in your stomach is because the plane is now lifting off and the back of the chair, the chair is like slamming into your back to shove you up, or the underside of the chair is slamming into your body, and your body is slamming into itself. Like now something was pushing you and trying to get you to do something unnatural, which is not have velocity, but change your velocity. And it's just as unnatural when the airplane tries to slow you down or bring you down. Like you feel fine when you're cruising at 0. You feel fine when you're cruising at 1,000. Cruising is cruising. Velocity of 0, velocity of 0 is the same state of affairs as velocity of 10. What you don't ever feel is velocity. What you always feel are changes in velocity because F equals ma. You feel forces. I don't know if that helps or not, but like, so you do, right, we don't feel that the Earth is moving. Okay, I'm imagining, right. Well, right. So what Gabriel, basically I'm agreeing with I'm agreeing with all of you, but yeah, like what Gabriel's saying is like good by me. Yeah, I think I want to be right. Okay, thank you. Right. So there you go. No, and it's good. Like if there's one thing science should teach us, it's open-mindedness and objectivity. If there's one thing we as scientists, and I'm not saying you all should, I'm not saying you all have to believe in shamans or religion or anything, like believe whatever you want, but just don't believe the hype. Don't believe that you have to believe certain things or that you're not allowed to believe certain things because you're a scientist. Being a scientist means that your jury is out until the evidence is in, that you believe whatever is the simplest, most productive view for you to have until the evidence contradicts that. Now, if you get evidence and it contradicts your belief, you should have the objectivity and the scientific like maturity to reshape your view and adapt it, as scientists have throughout the centuries. But you always have to know that you don't know what you don't know. Like that's what makes the great scientists great scientists. They never think they're at the end of the line. They think they've pushed the line forward, right? So yeah, and if there's one thing that all scientists, well, look, I shouldn't say that. All the scientists that I respect, or all my heroes, if there's one thing they all know, besides that the fact that they don't know what they don't know, is they all know that there's something more than meets the eye. We use the eye and the nose and the mouth and the ears because that's what we got. That is our input mechanism for getting the data from the world into our brain. Those are our mechanisms. That doesn't mean that they are the world. It means that that's how we get our data. And the reason we trust data is because other people can reproduce and back up the fact that we're not just like spinning our own wheels. But you should always recognize that there's more than meets the eye. And science is about using the eye to get to the more that meets the eye, not just to think that the end of the line is our eye. Like how dumb would that be? Well, I shouldn't say it, but right. So yeah, so yes, I thank you for feeling me, so to speak. Okay. Oh, okay, cool. Okay, sweet. God, I'm never going to grade these exams. It's going to be my fault. Okay, so Doppler effect. So actually, I've talked so much now. What I'm going to do, I'm going to go right back to the problem that I assigned you guys last time. I'm going to ask you to start working on it now. You may get stuck. It's totally okay. But it's probably time for me to shut up and put you to work. So, I'm just going to get back to, okay. Oh yeah, we said all this, but oh yeah, blah, blah, blah. Oh yeah, we did all that. Oh, that was fascinating. Oh, remember that? Oh, that was fun too. Oh, and then I said that thing and then you said that thing. Oh, right. And then And then Lars didn't move, and then Kat didn't eat a donut. Oh yeah, and then Veronica said that. Okay, cool. Remember? Oh yeah. And then Joe was good at chess, and then Lola was even better at chess, but he doesn't know that. Okay, and then that happened. What I'm looking. Oh yeah. So right. All right. So I just explained all that. Okay. Where I'm trying to get to here. Oh yeah. And then we talked about music. That was so much fun. Okay. Okay. So here, okay, we're going to get to the problem now. Like, again, there's going to be we're going to do a Doppler effect problem like you're going to do it. I'm going to set it up with the numbers. I'm going to set you up with case number one. I'm going to ask you to do case number one on your own, and then we'll check in once I think. Yeah. Once I think we've sort of got case one, then I'm really going to turn you loose and ask you to do all the rest of the cases on your own, following the same model. Okay, so here's the setup again. Like again, if you have your notes from last time, I'm not changing them, but we have a source of sound, which you can picture as a speaker. It's making a sound wave. On my piece of paper, it's going to the right. It doesn't, you can make it going to the right, going to the left, whatever. You can make it going up or down the page too. Gravity has nothing to do with what we're talking about here. Then you have this receiver over here to the right, which I'm sort of designating with a stupid cartoon version of an ear. So the sound waves comes out of the source. I'm going to give you the givens, and I'm going to ask you what to solve for. Let me remind you that in the ultimate thing of a Doppler effect situation, I mean, what makes the Doppler effect a Doppler effect is that a wave goes from a source to a receiver, but as long as the velocity of the source relative to the medium is different from the velocity of the receiver relative to the medium, as long as, in other words, the source and the receiver are in two different reference frames, like it could be sun and earth, or could be you and a car, or whatever, but as long as there's some kind of motion between the source and the receiver, then what happens necessarily in the Doppler effect is that whatever frequency the source measures for that wave will not be the same as whatever frequency the receiver measures. So now again, nothing interesting happens if the source and receiver are just sitting around. Then the source sends a wave to the receiver, and whatever the frequency of the wave is as measured by the source will be the frequency as measured by the receiver. But if there's any motion at all, then the source measures one frequency, the receiver measures a different, which means in sound terms or musical terms, just to remind you, right, that means that like one note would be heard by the source and a different note would be heard by a receiver. And this is like totally true in the sense that, if it's a car going past you, like blaring its horn, you could and we used to do this a long time ago before COVID, and when I was at another school, we would like literally get in a car. I mean, this was in New Orleans where you could do stuff like this. Like we used to do with a kid, we would there was invariably a kid with a convertible. Oh, convertible is a different issue, sorry. But we would do this where we would like get into a car and blare the horn in the car as the car drove past the school. And somebody in the car would have a tape recorder. This was in the days of tape recorders. And somebody standing on the street would have a tape recorder, and they'd both like record the sound. And then when we were done, I mean, the sound that was being made while the car drove past the street. And then when we were done, we would take the two tape recorders and bring them together and play them both at the same time. And there was two different sounds on the two tape recorders, right? So one thing I'm trying to stress here is it's not an illusion at all. It's totally real. But also, even though some people, this is called the Doppler effect, some people will call it the Doppler shift or the frequency shift. What I want to make clear is it's not that the sound like changes along its path from one thing to the other or something. It's not that. It's that the receiver and the source will experience two different sounds, two different frequencies. And in the traditional Doppler effect problem, what you're given is the frequency according to the source and the speed of the wave according to the medium. And you'll be given the speeds of the source and the receiver, and you have to find, and that's what you're going to do right here, you have to calculate or predict the frequency of the sound according to the receiver. So I'm going to, in our example that we're going to do right here, we're going to, and again, I know I wrote this down for you last time, but just to bring us up to speed, we're going to do you're going to do an example of case 1 here. By case 1, I mean the case where the case where the receiver is moving toward the source. That would be case 1. Case 2 would be the receiver moving away from the source. Case 3 would be the source moving toward the receiver. Case 4 would be the source moving away from the receiver. That is 4 different cases. The way you solve all of them is the same way. So once we get it down for number 1, you'll have it for all 4. But the results you'll get will be different, and that's what we want to see. And I don't really care which one we call 1 or 2. It doesn't. I mean, the names are arbitrary, but they are 4 distinct cases. So here, in our case here, here's the givens. I mean, they're written down right here, but the givens are, assume that we're talking about sound here. So we're going to assume that VWM, that means the velocity of the wave relative to the medium. So W stands for wave, in this case, sound wave. M stands for medium, which in this case is air. S stands for the source, i.e. like the speaker or the singer or whatever. Then R stands for receiver, i.e. in this case would be an ear or something like that. Sorry, I hear, do you guys hear? I'm hearing something weird while I'm doing this. I can't tell if it's, all right, I guess it's another apartment, sorry. Yes, no, it is ironic, and it's actually kind of spooking me out, but it is ironic, yes. I mean, this must happen all the time, but I've never, all right. Sorry, how many ADHD professors does it take to screw in a light bulb? Fish. Or that's how many surrealists does it take to screw in a light. Anyway, so this is how the notation works. Notice everything I'm writing down has 2 subscripts now. Like there's the velocity of the wave. So like in this notation, what I'm giving you is that the velocity of the wave relative to the medium is 340 meters per second. The velocity of the source relative to the medium is 0. So the source is just sitting there and it's making sound. The velocity, skipping down to the bottom line, the velocity of the receiver relative to the medium is 40 meters per second, right? So that's why we're going to have a Doppler effect. And the frequency of this sound, the frequency of the wave relative to the source, we're going to say is 440 hertz. Like we were saying last week, that's like a middle A on a piano. So these are totally realistic numbers, especially assuming that the receiver is like in a car, because like 40 meters per second is about 95 miles an hour. So, I mean, that's like fast, but it's reasonable and realistic for a fast car. And if we did it too much slower, we wouldn't see that much of effect in the numbers. But so these are reasonable numbers. The thing you're going to solve for, is the frequency of the wave relative to the receiver. You're looking for what pitch the receiver experiences. Again, you're going to do this, all of you, in a second, and maybe it'll be super easy based on what you did with Walters, but maybe it won't be, and either way is fine. A couple of hints I want to give you before you try to do this. Number 1, this is a major important hint or technique. Like I say that the velocity of the receiver relative to the medium is 40 meters per second. To be fair, what I'm really saying actually is that the absolute velocity, like I'm really saying that the speed of the receiver relative to the medium is 40 meters per second. Negative signs and positive signs are definitely going to matter here. And whenever we set up a Doppler effect problem, we give speeds and magnitudes. We don't tell you how to deal with the minus signs and the positive signs, because actually that is part of the challenge. That is the thing that requires thought. But there's a way to, so I'm not literally telling you that it's positive 40 or negative. I'm saying the number is 40, and it's going to be up to you to decide whether to make that negative or positive. But since this is our first case, I want to show you how you make that decision. And this is an important detail. It's a detail, but like people mess this up all the time. So I'm saying, if here's our setup, if you look at this diagram as the setup, you know, all velocities are relative. The law, like it's always up to us in any physics problem to choose what we're designating as positive and what we're designating as negative. And as long as we stay consistent with that decision, our answer should work out no matter what. Like this is the whole Galileo point. Well, so you can make whatever direction you want, positive or negative, as long as you're consistent with it. And as long as you're consistent and conscious, it'll work out right. But it's very easy to not be consistent or conscious. So a word of huge advice or strategy is the first thing I always do in any Doppler effect problem is I'm going to define the direction in which the wave travels. I'm going to define that as positive, like the direction that the wave goes from source to receiver, whatever. So even if on your page, you happen to put the speaker over here and the listener over there, that's like totally fine. That's okay. But I'm recommending as a strategy, make then that direction positive. Whatever the wave is doing, make it positive. In other words, the speed of sound is positive 300, the velocity of sound is positive 340 meters per second. And anything that happens in the problem from here on, anything that's going in the other direction, make negative. So to be clear and concrete, not to like give away the farm, but in this case, in case one, where the receiver is moving toward the source, what I'm really saying here is you should make that 40 negative, because the wave is going like this, but the receiver is going like into the wave. So again, this is a decision you have to make as the user or as a problem solver, but I'm recommending to you, call that 40, which represents the motion of the receiver, call it negative 40. Otherwise, you'd have to make this velocity of sound negative 340. Just you have to keep straight that the receiver is going one way and the wave is going the other. That said, you are solving for this. My very last hint or my very last guidance is that the way, well, I think I told you this last time. Number one, you're only going to use two equations and you're going to use them over and over again. One equation is v equals lambda f. That's how you deal with the velocity of a wave. The other equation is this VAC equals VAB plus VBC thing. You're just going to use those over and over again. And what do I mean by over and over again? I advised this last time, you're now going to do it. The procedure is, and it's maybe easier said than done, or maybe it's easier done than said, but my advice is first, look from the perspective of the source. Use the facts that you're given to get the wavelength according to the source. You do have enough facts to do that if you are careful. I would recommend bearing in mind both equations, even though you might think that you only have to use one of them. Bear in mind both equations, get the wavelength according to the source, then recognize or assert that whatever wavelength you got according to the source, that has to also be the wavelength according to the receiver. The one thing that's not going to happen ever is the wave is not going to shrink or grow along the way from the source to the receiver, because waves always travel at a constant speed relative to their medium. So you get the wavelength according to the source. You then believe that whatever you got according to the source must be the wavelength according to the receiver, and then you'll use that along with the two equations to get the frequency according to the receiver. I will tell you one last thing, and then I really will shut up for like 35 seconds, that you're looking to solve, and maybe some of you have already done this while I was talking, and if so, God bless you, then you're going to help other people in a minute, and or you're going to move on to case two. But in order to solve this, again, you all are looking for the frequency according to the receiver. That means it's going to be a number measured in hertz. It's going to be a number in the neighborhood of 440. Like we're playing in A here according to the source. The receiver is going to hear something in the neighborhood of 440. Like if you get 3,000, you've done something wrong. If you get the number 7, you've done something wrong. If you get a negative number, you've done something wrong, because frequencies can't make negative. I don't know what that would mean. That would make no sense. So you're looking for a number that is positive and sort of around 440, but it's either going to be a little bit higher than 440 or it's going to be a little bit lower. And the truth is, if you totally were paying attention last time, or if you could picture this whole thing, you could even predict that in advance. We are in this case one, the receiver is like running into the waves. It's like us standing at Coney, I mean, it's like us being at Coney Island or Rockaway Beach and running into the waves. I think we said last time what you would expect. I won't say it again right now, but I would expect that if I run into waves, they're either going to be hitting me more frequently than if I stood still or less frequently. But I think it's logical which way it would be. And I think you could picture that. So ask yourself before you solve, are you expecting a number that's slightly higher than 440 or slightly lower than 440? And that will be your check. But I've said way too much already. Again, what we're going to do, I'm not going to put breakout rooms or anything like that. What I'm going to, wait, am I? Yeah, for this one, for case one, I'm just going to shut up and let you all do whatever you want. You can work by yourself individually. You can talk to each other. You can chat. You can blah, blah, blah. But once you think you have an answer, like put it in the chat or whatever, or start helping other, like you self-manage. We will get more formalized about it in a minute. But just for this case number one, I'm going to mentally walk away. Like I'm going to start looking at your exams again. I'm here, but I will rejoin you mentally once I think you guys as a group have arrived at consensus for the answer. Like the answer you're looking for is the frequency of the receiver. So if a bunch of you think you already have it, then like wait to the other people to catch up or like check in with them. But like I won't accept an answer until I think that the whole group has confirmed or denied that they all agree with it or whatever, if that makes sense. So it's kind of like a board meeting that way. And I'll check in the chat. Okay. Okay. So does it make sense? So the task is, yeah. So okay, that is your task. I will shut up. Again, I'm not going anywhere, but I am mentally revisiting your exams. So, and you can use the chat and all that, but I will not interfere until you guys reach consensus. In fact, I will walk away for 1 second to use the restroom. Oh. Okay. And one thing, so right now on the screen is the numbers that I gave you, but I'm just telling you all that because I just shared the whole file, like all the notes from today, and which is also the same as last time. I mean, I shared them last time too, but I just shared the whole file with all of you. And the reason I'm telling you that is because once you copy these numbers down or whatever, and then I'm going to assume you have the file in your possession. And I did that because I'm going to turn off the screen in a minute because this screen is where all your exams are and stuff. So I'm going to be looking at so I'm going to turn off this screen sharing in a moment. So please get what you need or tell me what page you want to see before I do. But also I did just put the file in Google Classroom. But okay, hold on. Oh. Oh. Oh, sorry. Oh. And again, I see lots of progress is happening. I'm not trying to be cagey, but I'm literally not commenting until you guys, and maybe you are, but once you guys say, yes, we think we have an answer, then you tell me, and then I will weigh in. But like, I see things are happening, and I totally get that people have answers, but like, just let me know when you all agree as a group or not. Yeah. But until then, I'm just here.
Did anyone else get anything different than what people in the chat are saying? Or did you work the problem differently? I'm just curious. Oh, you're welcome.
And again, like, and I don't know how the board meetings go with with Walters, but like, even if like, it might seem very obvious that you're all saying the same thing or that you're all agreeing with Kat or whatever, and that may well be true, and it might even be right. But I'm just waiting for somebody. It could be Kat or it could be someone else to just say officially, like maybe what Kat or somebody should do is like literally take a poll, like, are we ready? Like, but I will respond once I'm literally explicitly told we are ready. And yeah, so that could be now, but I'm like, I don't want to interpret for you guys. So, and there could be still people still working, like, so I don't know. So it's up to you. Okay, so that's an official word from Jasmine. I'm taking that as the official word. Is that okay? Okay, all right, fair enough. So, and are we all agreed that the receiver is meant to be moving toward the source, right? Like that we're called just because we said so, not because it always is, but in this case, one, the receiver is moving toward the source, right? So, yes, agreed. Okay. So can I just add, not that I'm trying to be weird, and I'm glad you all worked so fast, and it sounds like you all agree, that's cool. And I like the sound of your number in a way, but let me ask this. If we were at the beach, like I'm standing there and waves are coming in at me, like every second one crest hits me in the face, then if I started running, if every second one crest hit me in the face and I started running toward the waves, would the crests hit me in the face more frequently or less frequently than one every second? And I'm not asking you to do math. I'm just asking you to like visualize, like it. In a way. Should I ask the question again? Like, you might think I'm sort of like being a teacher here, and I guess maybe I sort of am. Like, if I'm standing at the beach and waves are like, yeah, wave crests are coming in some kind of regular pattern. If I started running toward them, would I encounter them more rapidly than the original pattern or less rapidly than, like, would I get more frequently wet or less frequently wet? If I'm, so waves are coming in, but now I'm running in to meet them while that's happening. I'm asking anybody or everybody. And oh, thank you. Yeah. Okay. So like, right. I think I agree with what Quasi is saying. I'm not trying to trick anybody, but right. Okay. So I agree with what Skyla's saying and Veronica and everybody else. And so that's not a critique or a complaint. I mean, I think that makes, it's not meant to be a trick. I think that is right. I think it makes sense. In other words, if a receiver is approaching the source of waves, if a receiver is running into waves, it seems to me that the frequency received would be higher than the frequency sourced or sent, right? Or put it, if these were ripples in a pond and they were being caused by a rock dropped into the pond, like whatever number of waves were coming out from that rock, I think that the number every second that would hit me would be more if I was running toward the rock while it's happening. So what I'm getting at is I know the number that you got, I know it's reasonable, and I think you all did something very, very right. But I think perhaps the reason I'm asking you to think more is it seems to me that something is not right if you got a number lower than 440. I think you're looking for I think I would expect that the number you get would be higher than 440 because the receiver is moving toward the source. I think your answer might even be exactly right if we had said that the receiver was moving away at 40, but we're not. We're saying it's moving toward. And and again, one way to account for that, and you may or may not have done this, I didn't look at your work yet. Oh, and I should say, I am sort of following the chat, but I'm sort of deliberately staying at, above it. So I did not read Kat's, I did not look at the work. I just see the number. So I'm sort of deliberately not telling you where you went wrong in the work. One thing is, I do suggest that if you're calling the speed of sound positive 340, you should, or if you're calling the velocity of sound 340, I think you really want to make the velocity of the receiver negative 40. You may have done that, you might have, but then there's an error somewhere else. But I think you guys need to think a little bit more before, right. No, and you should picture, right. Okay. Thank you. No, and I am, yeah, like in order to predict what type of number you're looking for, picturing it is the right thing. But now that we've pictured it, I think it shows that somewhere in your math, something, you're not being dumb, like this is hard for a reason, but somewhere all of you, like, so rethink something or pass the work around or I don't think the answer is 389 is really what I'm trying to say. I think it might be that answer for some other case, but not this one. So I will shut up for a while. You probably did mostly, it's probably a minor error somewhere, but like work together or whatever. I'm liking what I'm seeing in the chat, but I'm very intentionally staying at, like, I think you are making progress, but I think you all do, like, don't look to me. Don't wait for me. Wait until you have, yeah, and even if you're wrong again, it's okay, but you guys really should, like, this is like a board meeting and maybe I should walk away, but like, feel free to talk or do in the chat. But again, what you're doing so far is good, but but pretend I don't exist. Like, this is science, right? Like, there is only what we figure out. So, I mean, some of you are involving yourselves and some aren't. So, call on each other or something. Or if you want me to make breakout rooms, I will. But I think you're on the right track. But I'm not going to, like, I need you guys to, like, literally notify me once you really think you have an answer. Or if you absolutely want to give up, I suppose you could tell me that too. But I'm really waiting until there's consensus. Um, I'll say this. I'm not trying to, all right, I'm going to help a little bit with this first one, and then I really am going to. So I'm going to say, wait, I'll look in the chat. I'm sorry, maybe. Okay, okay, let me help a little bit here. I don't mean to. So I think that I do agree with this new number, 493, but I think there's a little bit of a retrofitting going on here. Like it is the right answer, but I'm not sure if you totally see why. Let me start. I will run it through for all of you, and then I'm going to ask you to do the other cases. But I think the first thing to add, so I'm looking at Kat's, notes. I like it. Definitely, it's using both equations and all that. But I think one important thing is, what do you mean? Like, what do you mean by A? What do you mean by B? And what do you mean by C? Like, we don't want to just use the equations arbitrarily. You'll know how to use them if you're using them. Like what? Like when you. Let me just see if I want to say this. I mean, A, B, and C should stand for things such as receiver, medium, and source, or something like that. Yeah, so I guess my question is, what are you solving when you did when anybody, I mean, it's not just Kat. I mean, obviously it's her piece of paper, but when you used I think you guys want to make a conscious decision about what you mean by A, B, and C, and therefore why you're plugging in what you're plugging into in that VABC thing. I think I'll leave it at that for a minute. Just ask yourself what A, B, and C stand for. Okay, all right. I'm gonna. All right, I will. I'm not. I know I sound. I'm gonna. You're making progress, but yes, I think you guys are maybe diminishing returns. I'm gonna walk through the first one, and I'm also I want to get your exams back, but so I'm gonna walk through the first one. And it's going to be consistent with what I don't mean to wildly blow, like it won't be a wild departure from what Kat is saying in the screenshot or what you guys are saying, but I but I yeah, but I think maybe there's a gloss over going on here. So okay, so let me just switch screens. Give me 1 second. Oh yeah. Oh. Okay. No. I appreciate your honesty. Yeah, and I'm not even saying that there's I mean, it's like about decision making. I'm not saying it has to be one way or the other, but just okay. So all right. So I'm just going to walk through, and I don't know why I sound the way I do right now. I apologize. I mean, it's just late. I know that. I'm going to walk through the first one. Then I am going to ask that you guys take this and run with it to do the other 3 cases. Okay, but so we're talking about. Yeah, okay. Okay, so right, this is the setup here we have here, and again, so the speaker's making the sound. It's coming out the ear, which is like in a car or something like that, is driving toward the speaker, and I'm designating the direction of the wave as positive. So I'm saying that that wave relative to the medium is going positive 340. The receiver is going in the opposite direction, like toward the speaker. So I'm calling that negative 40. It's doing that relative to the medium. And the source relative to the medium is just sitting there at 0, right? Okay, and the frequency is 440 hertz. Okay, so that's my setup, right? And I'm solving for, like we always are in the Doppler effect, I'm solving for the frequency of the wave relative to the receiver. Okay, so what do? I first go to solve for the wavelength, like we said. Okay, procedure. I'm going to solve for the wavelength of the wave relative to the source. That's what I always do first. And this, by the way, I think everybody did this right, but I'm going to do it anyway. I want to get the wavelength the wavelength of the wave according to the source. Now, how am I using this? How am I doing this? Well, yes, I'm going to rely on the only thing I know about waves that's relevant here, which is that the velocity of any wave equals the wavelength of that wave times the receiver. But and I'm going to rearrange to solve for wavelength, as you did, as Kat did, as Veronica did, as everybody did. But let me be explicit now. And even this part you did, but I'm going to be explicit. Like velocity from here on in always has two subscripts. It's always velocity of something relative to something else. Well, here I'm looking for the wave relative to the source. So what's relevant here is the wave relative to the source. So I'm going to say the velocity of the wave relative to the source equals the wavelength of the wave relative to the source times the frequency of the wave relative to the source. I mean, to be even more explicit, that if I'm talking about the wave at all, if I'm talking about wavelengths or frequencies, the first subscript will always be a W. Like you can't get the wavelength of anything but a wave. But the question is it like wave relative to source or receiver? And right now I'm looking at source. So all my subscripts have S's. All my second subscripts are all S's, right? Okay. And again, this is totally what you guys did. I don't mean to say that this is, this isn't like weird or anything. And so I rearrange it just like you guys did. I say, okay, the wavelength of the wave relative to the source equals velocity of the wave relative to the source over the frequency of the wave relative to the source. Again, this is essentially what you guys did. Now I'm going to be careful. Oh, and even this part is what you did. I'm going to like plug in numbers, right, to get wavelength. Now, so the numerator says to plug in the velocity of the wave relative to source. Now, here's where, again, I do think Kat did this in the piece of paper, and I think Veronica, I mean, I'm picking people arbitrarily, but I think what I'm about to do, you did, but let's just be very clear and direct about it. Like the velocity of the wave relative to source, just to be as clear as I can be, we were not given that. We might think we know it. We might think there's only like one number to plug in for velocity here, and so we might all be plugging in 340, but let's just be very clear. We were never given the velocity of the wave relative to source. Well, so let me write that. Like we weren't given VWS. We were given VWM. And that's not because I'm trying to trick anybody, or that's not because it's like a weird exercise. This is the deal with nature. Like what we know, what is definitely true about any wave is the velocity of it relative to its medium. Like that, like backing up again for a second, like with baseballs, we couldn't even do a problem like this. It wouldn't even make sense, because no one just like automatically knows the speed of a baseball. Even if you know you're throwing it in air, a baseball could go any speed relative to air, right? So the only way we could know it is if we actually measured it or clocked it in a particular case. But with a wave like sound, we actually know before we even begin the problem, just by specifying the medium, by saying, okay, it's air at standard temperature and pressure, we automatically know going in this 340 number. But the three, and like I gave it to you, but the reason I could give it to you is because it could be given, because what is an unbendable fact of nature is that relative to the air, this sound will travel at 340 meters per second, relative to the medium known as air. That's what's given in the problem as VWM. Explicitly speaking, no one told us the velocity of the wave relative to the source. Again, it might seem really easy to figure out right here, and it is exactly what you guys think. But please note, it's actually something we have to take a step to figure out. It is not given. There's no law of nature that says that sound has to escape a speaker at any particular speed relative to that speaker. Okay. So what I'm saying, we don't know we need VWS here, but we don't have it. What we have is VWM. So what we can do, and again, this is in effect what you did, but this is where you sort of like did it with A, B's, and C. So I think in a way there was like a little fudging or a little like hopeful guessing going on. And obviously I'm impressed. I mean, I don't mean to criticize anybody, blah, blah, blah. But like what on the next page, what I'm saying is we don't know VWS. We need it for the numerator of that fraction. We don't know VWS, but one thing we do know is like just pretend W and S are A and C or something. Like if I don't know the velocity of me relative to New York City streets, but I do know the velocity of me relative to a subway, And if I do know the velocity of the subway relative to the streets, then I could get it. In other words, like this is one statement that is definitely true. What I just wrote, like it looks like I just made that up, but I'm just following the pattern. Or put even more rigorously, what I'm saying is, in effect, I'm saying, okay, and this is not disagreeing with what anybody said. I'm just trying to explicate it. I'm saying, look, let A be the wave, let C be the source. Well, we want the velocity of the wave relative to the source. We don't have it. But if you let A be the wave, C be the source, and V medium, or put another way, just recognize A, B, and C were not special. They were just arbitrary letters that just meant any three objects. The point is like the pattern of how the letters are arranged, or what some of you called last week, like transitivity or whatever. What I'm saying is velocity of wave relative to source, what it must equal necessarily is the velocity of the wave relative to the medium plus the velocity of the medium relative to the source. By the way, for that matter, I could also say, something like velocity of wave relative to medium equals velocity of wave relative to source plus velocity of source relative to medium. Like there's a ton of combinations I could say that would all, I could also say for that matter, I'll do one more. I could say velocity of wave relative to source equals velocity of wave relative to some egg plus, I'm not trying to be weird, but, and this may confuse people in their notes if they don't know what I'm doing here, but I'm saying what's true about velocities is this pattern. Like if you have three objects, the way velocities add among those three objects is this way, no matter what. It's super obvious in the obvious cases. Velocity of me relative to subway plus velocity of subway relative to streets equals velocity of me relative to streets. Like everybody knows that in their mind, so much so that like they wouldn't even pay attention to this if not, forced to. And you especially know it if one of the velocities happens to be zero. What I'm saying now, though, is that it's always true. And I could put in that, I could say VW, if I don't know VWS, I could say something like at the bottom of the page, VWS equals VWE plus VES, where E stands for some egg. That statement would be totally true. Only I'm not going to write it down because I don't know anything about the egg. It won't help me here. But like it's true. It's just not relevant. Similarly, I could write down something that seems more relevant. I could write down velocity of wave relative to medium must be equal to velocity of wave relative to source plus source relative to medium. Like as long as it conforms to this pattern, it's true. But again, even if I wrote that down, the thing that's at the bottom of the page here, even if I wrote that down, it'd be true, but it wouldn't really help me much because what I'm looking for is the velocity of wave relative to source. So I write down a version of Galileo's principle of relativity that will actually help me here. Again, I'm yelling because I'm excited, not because I'm angry at anybody. But and also I'm yelling because I'm frustrated myself that I'm not going to be giving you your test back. But I'm moving fast with them the truth is even when you were just sitting there for 5 minutes, I'm moving pretty fast. So you will get them soon. And I do apologize. But anyway, but so here I'm literally writing down VWS equals VWM plus VMS, both because it's true. It's one of 50 different true combinations that I could write down, but also because it's a helpful, relevant one to write down. I'm looking for WS. What I actually know, or what I was given in the problem, is WM. So this looks like it's going to help me. Now I'm going to take I'm looking at the time. Okay, I'm going to take and again, I know this is so far, it's totally consistent with what you guys were doing. I'm just spelling it out more carefully so that we know what we're doing and we can use it in the other three cases. So I'm going to the next page. I write down VW, and this is all still part of step one, where I'm solving for the wavelength of the wave according to source. I'm going to get an answer that is exactly like the answer you got. It's going to look like you got it much faster because you did, but you need to like walk through this whole thing so that you can see it for all cases. Well, you'll see. So you can see why your answer was right. So I write VWS equals WM plus VMS. Again, that's true, and it seems helpful because I'm looking for WS. VWM, I know, like that's what was given in the problem as 340 meters per second, and specifically positive. VMS, now let me think about this in English. VMS, like I just wrote it down because it worked with the pattern, but what does it mean? It means velocity of medium relative to source. Velocity of medium air relative to source, i.e. relative to the speaker. Now that's a thing, that's a real concept. How fast is the air moving relative to the speaker? Now, like I think many of you know the answer, but I'm going to say it my way. You might say to yourself, with velocity of the air, he never said the air was moving. Like, what do you mean velocity of the air? You mean there's wind? What are you doing, Yaverbaum? No. I'm not saying the velocity of the air relative to planet Earth. You're right. I never mentioned, like there might be wind, but I never mentioned it. We don't know about it. Like that would be unfair for me to just like introduce here. But that's not what I'm talking about, because the Earth has nothing to do. It's not an object in this problem that anybody's concerned with. I'm saying the velocity of the air relative to the source, like velocity of medium relative to source. Well, what the heck is that? Someone might say, well, I mean, it's not, I mean, you may already know it, but just in case you don't. Well, one way I could know what the velocity of the medium relative to the source is, I know necessarily from Galileo's principle that whatever it is, it must be the opposite of the velocity of the source relative to medium. Again, I'm saying that almost as a foreshadow to the next part. It's like, if I say what's the velocity of the air relative to the source, don't think we're suddenly introducing some new concept of motion or something. I'm talking about how fast is the air moving from the perspective of the source, and what that is necessarily just the opposite of whatever the source is doing relative to the medium. And that we were given. We weren't explicitly given VMS, but we were given VSM. We were told that it's zero. Like the source is not moving in the air, right? Therefore, I mean, again, I'm dragging this out in the simple case to show you what to do in the complex case. But if you were given that VSM is zero, then I do think that that means that VMS, like what we're being asked for here, just from the pattern, is that velocity of the medium relative to the source. In other words, the air speed relative to the source. Oh, it's zero. There is no wind relative to the source because the source is just sitting there in the air. Like I think many of you knew, like I saw it in Kat's page. Again, but so that means, okay, in this part of the problem, I'm going to put in zero for there. What I'm really trying to say by dragging this all out is, yeah, it's just going to be zero, but it's zero because it is zero, not because it's always zero. Like in order for me to do each one of these steps, I always have to check Galileo's principle of relativity. Right here, that second term is going to be zero for sure, but I don't know that until I know that. Like it won't be in the next part of the problem. So now I can say, aha, VWS, by the procedure, VWS, the thing I'm looking for, equals in effect 340 plus zero. Okay, so as you guys thought, it equals 340. In other words, I'm saying the velocity of sound relative to air is always 340. And in this case, that means the velocity of sound relative to the speaker must be 340 because the speaker happens in this case not to be moving through the air. Okay, so VWS is 340. Why did I do all that? I did all that so I could plug it into, like I did all of that work, or I over-explained all that work because I needed that term to plug into this fraction. Now I have it. Now I'll plug it into the fraction, again, like you guys did. So I can say, so this is all still part of step one. Step one, in effect, like, if I weren't talking so much and you're just doing it on a piece of paper, you'd be right to think what you guys did on a piece of paper, which is each one of these steps is basically the two equations. And that's all I'm doing here is the two equations. I'm saying lambda V WS equals V WS over FWS. And that FWS, that was given as 440. So, okay, so now I can say, fine, 340 meters per second over, it was, well, yeah, over 440 hertz, which is really to say cycles per second. So the cycles cancel out. And we do get, indeed, as you said, 0.77 meters is the wavelength of the sound according to the source. Now that was all step one of the procedure. Just looking at the time. Okay. So the wavelength, which again, you got, and that's awesome. So what we're saying here is, okay, just according to that, we apparently have sound traveling at a wavelength of like, 3/4 of a meter, which again, by the way, to go back to last week, that is a realistic number. And it's kind of like, just note, it's a very macroscopic number. We're saying that if you play an A on the piano, it creates ripples through the air that are like 3/4 of a meter apart. Like that's like very, real and measurable. But anyway, we got that. So now what do? Now we say step 2 of the procedure is we recognize, okay, that now like ripples are traveling through the air across the other guy. They're going to, and they're like, 0.77 meters apart. They're going to continue to be 0.77 meters apart as they travel. Just like if you were at the ocean, the waves are coming towards you. They're each like, say, a meter apart. Even if you start running into those waves, something funny is going to happen. They're going to hit you more frequently, but they're not going to get any closer together or any farther apart. They are what they are. So like some things are like the whole expression, it's all relative, baby. Yeah, awesome expression and hilarious. But actually, the lesson in all this is not that everything is relative. Not everything is relative. What's relative is velocities. And therefore frequencies, but not like accelerations are not relative, but velocities are, and therefore frequencies are. So we have this. So now I go to step 2 and I say, okay, wavelengths are not relative. Whatever the wavelength is at the receiver must be the same necessarily as the wavelength measured by the source. So necessarily, okay, we now have inferred that the wavelength, according to the receiver, is approximately 0.77, and approximate only because we're chopping off digits, not because like we're making an error or something. So that's step 2, and it's like there's nothing to that step at all. It's just an assertion that the wavelength is going to remain constant. So now we go to the receiver. And this is the final step. We're now going to use that wavelength that we just got. And let me back up for a second, back to step 1. I will go back to page in 1 second. Just want to, in step 1, when I say step 1 solve for lambda sub WS, to be more explicit, what I really should be saying is use FWS in order. So just to show you what we're doing, in step 1, we use the given frequency according to the source in order to solve for the wavelength according to source. So then we get the wavelength according to source, and now in step 2 we say that must be the same at the receiver. So now we go to the receiver and we're going to go backwards. We're going to use that wavelength to get the frequency. I'm going to say that one more time because once you just starting to get this, it seems like a circle. We use the frequency according to the source to get the wavelength according to the source. Then we take that wavelength over to the receiver and we use the wavelength according to the receiver to get the frequency according to this receiver. It seems like we're just going 2 steps forward and then the same exact 2 steps back. And we are conceptually, but the big difference is that the velocity according to the source is not going to be the same as the velocity according to the receiver. They're going to differ. And the only way we'll ever see that difference is if we use that Galileo step carefully. Right, and so here we go. I'm going to use wavelength according to receiver to get frequency according to receiver. In other words, I'm going to say again, velocity of wave according to receiver must equal wavelength of wave according to receiver times frequency of wave according to receiver. So the exact same equation that I did in step 1, only now with all R's instead of all S's. So I'm like rearranging and saying, okay, FWR must equal VWR. VWR over lambda WR. and I'm going to plug in this lambda WR that I just got, but that's the same bloody lambda that we had over at S. So this would just be one stupid circle if I weren't careful about the velocities in the numerator. The velocity in the numerator like this is where all the subscripts and whether you call them A, B, C, or what, come into play in a very important way. We were not given. Like if you're not careful about these subscripts, it's easy to think that you know speed, like that you know the speed of the wave. It's 340. What you know is the speed of the wave relative to the medium. You don't know it relative to the source. You don't know it relative to the receiver. That's what you figure out using Galileo's principle. So I'm going to do again the exact same thing we did before. I say VWR, I don't know, but I know VWM, that's what's given. So I could say something like VWM plus VMR equals VWR, just like we did in the step one. In step one, we did it and it was like easy and fast if I didn't talk so much, because it turned out that one of these two terms was zero and we just like crossed out, and so that it went away and it looked like it was never there. But I don't think either one of these is going to be zero this time. I think we want to be super careful. Like VWM, sure, we know. Oh, well, let me change it. Well, sorry, the color's all getting messed up. But like this, sure, is still 340. It has been, it remains, it continues to be. This VMR, okay, I was not given that. That's the velocity of the medium relative to the receiver. I wasn't given it, but I was given the velocity of the receiver relative to the medium. Like I have to say VMR must by definition equal the negative of VRM, and VRM we said was itself already negative 40. Like VRM, the velocity of the receiver relative to the medium, was going toward the wave source at 40 meters per second. We call that a negative number. So we want negative 40 here. And that is to say 40. So I'm going to put 3. So that's the number to plug in. I'm going to put 380 over the 0.77, which again is what you did, but here's like why it was right. And then when I actually do that, yeah, I'm sure I get the same thing here. In fact, I'm not even sure this was the answer that you guys got, but and it's not a big, it's a slight shift, but not. That's the answer, 442, and I'm not even sure if that is the answer that you put in the chat or not, come to think of it. Oh, wait, did I do math? Did I do math? Wait, did I just make an error? 380. This is the right procedure, but did I 380 380. And we said 40, right? So 380 over. Oh, no, sorry. No, I just did the wrong. I'm sorry. No, I'm sure your number is right. It didn't look right to me. 3. Yeah, sorry. No, you're right. 494. Sorry. Absolutely. That's better anyway. That was weird. That was that. But yeah, now I know I sound all teachery and stuff. So wait, yeah, I do agree with the number 494. Notice it's higher than 440, but notice it's higher for like, not because I retrofitted it, but because it conformed to this Galileo thing. Here's the thing. I know we have like 14 minutes. What I would really like is, like, I'd like you to at least do the next case. Well, no. Well, yes, do the next case. But here, to make sure we really see this, since we have limited time, I know it would be unrealistic to get all 4 cases this period. But what I want everybody to do in the 15 minutes, and I'm not going to do it anyway, like talk to each other or what, but I want you to follow this exact procedure carefully, like use this exact procedure. I want to, like, case 2 would be the receiver moves back the other way. And honestly, that answer will be what you originally thought was the answer. We can go back over it, but it's just what you would think. It's going to be this amount lower than 440 rather than this amount higher than 440. But I want, in the 15 minutes we have left, to make sure that we actually really get this concept, I want you guys to take all the same numbers, like I'll write it on the next page. I want all the same numbers, but now imagine that it's the source moving toward the receiver rather than the other way around, and follow the procedure to, so I will shut up in a second. And if this is the last thing we do, it will be totally worth it. Like same situation, only now we're saying that the velocity of the source relative to medium, we're going to call 40 meters per second. And I'll tell you right now to help, that's positive, because assume the wave is going like this positively. I want you this time to assume that the speaker is going toward the receiver, i.e. sort of traveling in the same direction as the wave. That's why I'm making both positive. So the speaker is going like that. The speaker is going forward while it emanates or transmits this wave toward the receiver. So assume that the source is traveling through the medium at plus 40. Assume that the receiver is just sitting still in the medium. So it's exactly the same as before, but flip. Assume the velocity of the wave relative to the medium is still 340 meters per second, which you can still call positive, and assume that the frequency of the wave as transmitted by as measured by the source is 440 hertz. So I'm going to tell you so this is what I want you guys to solve right now as a class or whatever, but I'm going to tell you 2 things. Like it's not a trick. You're going to follow the exact same procedure, and if you get the procedure and you're careful, you'll get the right answer. But here again, here we have approach again. Like the source is making waves, but it's running toward them as it makes them. So I'm going to tell you right now, I think, again, the frequency is going, the receiver is going to measure a frequency that I'll tell you right now, I would expect it to be higher than 440 again, just like before, because again, the 2 things are coming together. They're not going apart. But I don't think you're going to get the exact number that we just got. Like I would expect that you're going to get something higher than 440, but I don't. Oh, cool. Okay, cool. No, I'm glad. And I'm sorry but good. So now try it on your own, but do it this time where the source is moving. If you visually picture it, you would be right to think that again, the received frequency will be higher than the source frequency because in effect, these 2 things are coming together again, rather than going apart. but I don't think you'll get the same answer as before if you're careful and follow this procedure. So I will shut up. I know we have like 10 minutes. Do your best. I will tell you the right answer before we go, and that will be it. And I'm sorry about your exams. I will keep trucking them, and I'll get them to you. Like, I won't make you wait till all next Monday, really, because I can't stand it anymore either. But maybe you'll even have in time for Wednesday. Maybe anyway. But we've got 10 minutes. I think it's 10 minutes. Is it 10 minutes? Yeah, 10 minutes. So please try this one. And I will even maybe walk away. That's the other problem. I know with me being here, it's harder for you to focus also, but. Oh, 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 cool. Oh, Veronica. Okay, good. All right. Just by mere virtue of actually, that sounds good to me. That's cool. All right, I'm going to quickly do, but that's good. That's good enough for me. I know we have 3-4 minutes, so I'm psyched that anybody's trying anything. I know it's a long day, blah blah blah. But good, Veronica. No, no, no. But that okay. So I'm going to just do it quickly now. I'm going to just ask people to copy this. I mean, hopefully you'll. Well, anyway, I'm just going to do it, and I'm going to try not to talk because there's 3 minutes. So here we go. But please do copy this, folks, or whatever. I am going to trust though that like if we put this on with these two cases, I really think you guys can get the other two cases by just appropriately changing certain pluses to minus signs. Oh, I have to say something really important before I forget. There's a formula for all this on the web, like a Doppler effect equation. I'm telling you right now, do not rely on that or use it on the exam. It won't. It like anybody who's not paying attention is going to fall into that trap. You got to do it this way on the exam. It's like all. So if you heard me, good, but that equation that's all over the web is garbage. I can explain why later, but just this will separate the wheat from the chaff right here. Don't use the Doppler effect equation that's all over the web that has pluses and minus signs in it. It's completely anyway. But okay, here we go. I've gone to the next page, sorry. Oop. Okay, I know I'm going to flip page. Of course, I'm going to give you this file and everything, and I'm going to turn the pages back in a second. And of course, after all this, we run out of time. But so maybe Veronica's answer might have been a little bit off, but look, and I know we all have to go. I want to go too. So I'm going to keep you like 60 seconds. Obviously, if you have to go, but 60 seconds here. First of all, the answer I think is 500. You could check. Yeah, it's 500 hertz, which notice is higher than 440, but it's not the same as the answer we got like 5 minutes ago. So, and this is the complexity of relativity. We'll have to pick up on this more next week. But like what I'm saying is, if the receiver is moving toward the source, physically or visually, you might picture it as the same as the source moving toward the receiver. But there's a medium in between. So what's really happening in the other case, what happened was we sent a regular 0.77 wavelength toward the receiver, but the receiver was running toward it. So it got that wavelength a lot more rapidly than the source sent it. So it got a higher frequency. Here, what's happening is we're sending out the wave, but as we're sending it, we're running into it as the source. So if you look at our math, like I did the exact same procedure, but like right in the first step where we had to find the velocity of the wave relative to the source, right off the bat, it's not 340 anymore. It's 340 plus, in this case, a negative, like it's 340 plus negative 40, in other words, 300. In other words, I'm sending out the speaker is sending out this wave at 340 relative to the air, but it's running through the air at 40. So the wave is only running away from the source at 300 meters per second, like fundamentally different from the other case. And therefore, like every time we send out a little wave crest, we run toward it. So all the wave crests are closer together than they were in the other case. I'm not saying they're changing while they move, but in this case, we send out a smaller wavelength than before, but it's received by a receiver that's just sitting in the air. So in other words, in case one, we send out wavelengths and someone runs toward them to receive, and they get it there, they receive more frequently. Here, we send out smaller wavelengths and someone stands still to receive. So in the first case, the wavelength was just as expected, but someone ran toward to get it. The velocity was different, and therefore the frequency was different. Here, the velocity was different right at the source level. So the wavelength right from the get-go was different from otherwise. Like we're sending out a compressed wavelength, but then it's received at a normal velocity. So in one case, it's a regular everyday wavelength being received by a moving target. And here it's a not regular wavelength being received by a regular target. Two completely different logics, but captured by the exact same solution procedure, captured by the same steps, but they yield different answers. Both answers higher than 440, but higher by different amounts. I've gone over time. I totally owe you your exams. But please, keep this. Obviously, I'm going to put the file of these notes in your thing. This will be on the final exam for what it's worth. Not trying to scare it, but okay. Thank you for your attention. It's been a long day. I went 4 minutes over, so I also owe you 4 minutes of your life. But I hope this is somewhat clarifying or direct. I hope it's clear. I hope. Goodbye. Yes. Okay. Good. Okay. Good. Have a good week. Cork, bless America. You are very good people. Thank you very much. Goodbye. Don't ever change. Keep rocking in the free world. Okay. Bye. Yeah. Good. Okay. Thank you. That's very nice of you to say. Cool. Okay. Sorry. I'm sorry for everything in the universe. Oh no. Oh, I like that. I don't get it. But oh no. Oh, I do get that. My son explained it, I think. Thank you, Crystal. Okay. Cool. Okay, goodbye. I think I get hardcore. Okay, you guys are all good? Okay, goodbye. Thank you. Awesome. Thank you. Awesome. Okay.